This is lesson 1 on our DC circuits unit. We're going to be talking today about electric current. And current is, in electricity, current is a lot like current of water. That is, when we think about current in water, we understand that water is moving. In the same way, when we talk about current in electricity, we're talking about the same thing. Electricity is flowing. And if electricity is flowing, you have a current. And so some basic terms here. A charge, we use the letter Q to denote charge. And do you remember when we were in the static electricity unit that we used the same thing? We use Q to denote charge. Same thing here, same letter. It's a characteristic property of some elementary particles, that is protons and electrons. And again, back to our unit in electrostatics, we talked about protons and electrons. And then the same concepts there as well, that like charges repel and opposites attract. And the amount of charge is measured in coulombs. And so again, that all should be review from the unit that we did on electrostatics. We're coming back to that now. Okay, with current, we use the letter I to denote current. And it stands for the amount of charge that flows by an area in a unit of time. So getting back to that analogy of a river current, we talk about river current, how fast is the water flowing? It's how much water is flowing over time. That's what we mean by current. Whereas when we have electrical current, it's how much charge is there over time. But it's the same basic principle, that you've got these charges flowing through a given area, just like you've got certain water flowing through a given area. Couple things just to note here, make sure you don't forget that I stands for current and Q stands for charge, because those letters aren't obvious. So with that then, all of that information we can put together in a formula here, which is that I, which stands for current, is the change in charge over the change in time. And so we'll be using that a little bit in our discussion of current. Current is measured in coulombs per second, also called amps. So if you are familiar at all with any kind of electricity, you've probably heard of amps. And what amps are measuring is how much current there is, how many coulombs per second. And what I mean by how many coulombs per second is what is moving through, let's say this is a wire. All right, let's say this is a big wire and I've zoomed in on this wire, and we have several negative charges moving through here, and they are moving from the negative on the battery, or in the, I said battery, sure, let's call it a battery, to the positive on the battery. And as they are flowing, that is the current. And so coulombs per second, remember each of these charges, like back to electrostatics again, we would have one little charge and we would say there's a charge and it has 1 coulomb. That's its current, that's how much charge it has. And so each one is a charge flowing through, and how many are going per second, that is coulombs per second. That's called an amp. Okay, also back to our electrostatics unit, we learned that 1 electron has a charge of 1.6 times 10 to the negative 19th coulombs. And that number, if we need it, it is on your AP sheet. That's not something you have to memorize. But I'm bringing that up because this first question is going to ask about that. If we have 1 amp of current, that is enough to stop a person's heart from beating. If 1 amp of current were applied across a person's heart for 0.05 seconds, how many electrons flowed through the heart? Okay, well, we're going to go up and use that formula that we had just a minute ago, this I equals delta Q over delta T. Okay, if we use that formula, the amount of I is current, and that's measured in amps. When we have 1 amp, and how many electrons flowed through the heart, that's what we're looking for. And the time is given as 0.05 seconds. And so we can solve this and solve for Q, and we get delta Q is 0.05, And what do we measure that in? We measure that in coulombs. Now that's how much charge flowed through. The question was how many electrons flowed through. And so we need to continue on with our problem. We're not quite done. If we have 0.05 coulombs, let's do a little bit of a dimensional analysis and figure out if that's 0.05 coulombs, and we know that one electron is equal to 1.6 times 10 to the 19th coulombs, then the coulombs are going to cancel each other out. We're going to take out our calculator and we're going to multiply that together. And so we get our calculator and we get our answer to be 3.125 times 10 to the 17th electrons. And so just to kind of review what we talked about, we've got an amp of current flowing, applying to a heart, so it's going to flow. How many electrons flowed through the heart? Well, so we used our formula. We solved that for the Q, that's the charge, and the change in charge was 0.05 coulombs. Well, 0.05 coulombs, how many electrons is that? And so we went ahead and multiplied that out, and we came up with 3.125 times 10 to the 17th electrons that flowed in that time of 0.05 seconds. Okay, let's talk about the phrase potential difference or voltage. These three terms, potential difference, voltage difference, and voltage drop, they all really mean the same thing. It is the difference in potential energy per unit of charge. It is caused by an imbalance of charge, and it is the push that drives the electrical current. So let's go back up here to the diagram that we had a minute ago. It's the difference. Like if there was no difference between the amount of charge on this end compared to the amount of charge on this end, these electrons wouldn't have any reason to move. They're in equilibrium. And so they're not going to move anywhere. But if we create a situation where there is a difference, then those electrons are going to move, right? They're going to want to go towards the positive charge because they want to create that equilibrium. And so that difference in charge is called voltage. And all it is, it's the difference in charge between one end and the other end that causes those electrons to move. And without that difference, things wouldn't move. There would be no current. We talk about potential difference. Like I mentioned a minute ago, it's measured in volts. It can also be called joules per coulomb, but we don't really say that. We call it volts. But if you're doing a problem and at the end of the problem you end up with a unit and your unit is joules per coulomb, that means volts. And so sometimes it's just handy to know that so that you can do some conversion back and forth if you need to. The potential difference may be provided by a Voltaic cell. That's just a battery. And so a battery, you know what a battery looks like, and it has a positive side and a negative side. And so you've got your battery here, and one side's positive, one side negative. That difference is what causes the electrons to flow. And without that difference, electrons would not flow. And flow, I use that word flow, but that's current. That's current. That's what allows the electricity to have a current through there. And so what do we need for current? We need a potential difference. Again, if this was just equal on both sides, it wouldn't go anywhere. So it has to be different on each side. That's called potential difference. It needs to be a charge capable of moving. Remember back in our electrostatics unit that we talked about how things in insulators, electrons don't move very well. Those charges aren't going to move very well. But if they are in metal things, copper wire, things like that, they will move. And so the charge has to be capable of moving, there has to be a potential difference, and there has to be a complete circuit. And we'll get to that in just a minute. But like if you have, an example you would be familiar with is, let's say you have a light bulb. This is the inside of the light bulb. If you've ever looked inside of a light bulb, there is a filament. And the filament is this little tiny wire. And as long as that wire is connected, the light will turn on because there is current. If there is no connection, though, then there is no current, the light will not turn on. So that is a complete circuit. If that little wire called a filament If that little filament is connected, that is a complete circuit, and the light bulb will work. If there is a break anywhere, you will not have a complete circuit, and it won't work because the current won't have anywhere to go. Current's not just going to, it's not like a hose. I've been talking about water, but if you had a hose, this is the end of your hose, you're going to have water just like spurting out here, right? Well, current won't do that. If the end has nowhere to go, the current's just going to stay inside the hose and just stay there happy as can be. It's not going to spurt out. All right, so you have to have a complete circuit. Okay, this is a historical note, and if you watch the crash course video, I think she talks about this in the crash course video. Moving charges in any electrical circuit are the electrons. We talked about that a lot in the electrostatics unit. It is the electrons which move. Protons do not move. However, Ben Franklin actually thought that the protons moved. And so the directional notation for current was actually first thought to be the flow of positive charge, since a net flow of negative charge in any one direction is the same as a net flow of positive charge in the opposite direction. Because of this, by convention, all current arrows will be drawn in the direction of the supposed positive flow. And you can again blame this on Ben Franklin. He thought the protons moved. We finally figured out, nope, it's not the protons, it is the electrons. However, by the time that was discovered, so much had already been written about electricity that there was no way to go back and change all those books. So we just said, you know what, we know this is the way it is, but we're going to stick with it even though we know it's wrong. And so when we draw our current, they'll be drawn in the direction of the supposed positive flow. Let's turn the page. Okay, let me go back to that diagram we had on the other side. Let's say this is your wire. And let's say you have electrons flowing through your wire. As it is now, there's no potential difference, so they have no reason to flow. But once you complete the circuit, so you flip on the switch or whatever, then that allows these to start flowing. And it flows instantaneously, one electron in, one electron out. In other words, when you turn on your light switch at home, the lights turn on pretty much instantaneously. Now, the new light bulbs are not as fast, but it's like a fraction of a second that takes. The reason is, it's like a traffic jam. Let's say this is a traffic jam, and all these cars are lined up in the traffic jam. And they're trying to, well, right now they know they can't go anywhere, so they're just sitting there. They've got their car in park, and they are just sitting because they know they cannot get anywhere. But as soon as whatever is happening here goes away, those cars are going to start moving out. But these are not cars, they're electrons. And so they kind of push each other, kind of like bumper cars. And it's kind of like a wave. Almost like the Newton's cradle balls that we looked at, that they hit each other and this one hits it and this one hits it and this one hits it and this one hits it. And so it's happening rapidly, but this electron is going to pop out, whereas this one in the back, it's actually moving pretty slow. It's going to this position and then this position and then this position. It's bumping its way up, but it itself is not just flying out. Now, the electron flow is, the train is moving, so they're all coming out. But each individual one is just kind of bumping along. And I should say, and I think we mentioned this in the electrostatics unit as well, it's not like they're nice little all in line like a traffic would be. Like in the traffic, we stay within the lines, right? Here, there's a lot more random movement going on. And they are bumping each other, and finally coming out. But there are so many of them that they're going to start moving pretty quickly. So, the current flows nearly instantaneously. You flip on the switch, it turns on, but each electron is actually moving along quite slowly. Now, the more push or voltage difference there is, the faster the electrons will flow. And so if you have a high voltage, these are going to flow really quickly. If you have a low voltage, they're going to come and just kind of have their sweet little time and just kind of move along. The amount of voltage difference is what dictates that. If you have a low voltage, they're going to move slowly. If you have a high voltage, they're going to move much more rapidly. It also depends on the size of the hole the electrons are being pushed through. In other words, the cross-sectional area of the wire. So let's go back to our water analogy. If you have a big tube, the water can flow through there. Here's my tube. The water can flow through there really easily. If you have a little tiny drinking straw, that water, there's not a whole lot of water, it's going to slow down a lot slower. So with a larger wire, you will have faster current. It's like if you, again, back to the driving. Would you rather drive on a highway or would you rather drive on a small little country road? The highway is going to be a lot faster. The country road is smaller and you don't have as much space, so you're going to go slower. All right, we are going to get to drawing some diagrams. And when we draw those diagrams, we draw in the battery symbol and we draw in the electrical circuit. And so what I've drawn here is like the circuit. Like, let's pretend this is a piece of wire and it's going around. And I need to connect that with a battery. That battery is going to create the potential difference. And when I draw this, there are a couple different ways you can draw it. I'm going to draw this one just so you can see what it looks like with a positive and a negative. So this is the positive and this is the negative. The longer line is the positive pole, the shorter line is the negative. And so that would be a single cell battery right there. Each little pair like that is a single cell battery. And something like a AA battery, that's just a single cell. So if we just have a AA battery, it's just drawn like this. Now over here, you don't have to draw these, but I've just pulled these out so we could look at them. What we have here is, here's our battery. Notice it says 9 volts and it has a couple of lines. It goes long, short, long, short. And so that's implying that that is a 2-cell battery. Again, here is our battery, long, short, long, short. My point in showing you these is mainly to look at the battery. And again, the battery is this piece of it right here, or right here, or right here. Oftentimes in physics, we just draw one positive and one negative, and that's all we need. Sometimes you might draw in more. If you have several batteries, you would draw in several pairs. And so if you're taking an electrical class over at the center, you might be drawing them more like this. Our physics textbook typically just uses one single pair because that's all you need is a single cell to cause a voltage difference to create a circuit. But that's just how we draw them, just so when you see these drawings, that's what we're talking about. Okay, let's look at this next example. A battery is used to create a current by providing potential difference across the wire. Draw in the direction of the electric current on the diagram below. Okay, so here we have a diagram. What this is supposed to be is like, let's say this is a 12-volt battery. So that's our 12-volt battery. We're going to call this our positive and this our negative. And then we're going to say this is our device. And when I say device, I mean it could be anything. It could be a light bulb, it could be anything. In this class, typically we will talk about light bulbs. So you have a battery, you've connected some wires, and it's lighting up a light bulb. So in this case, which way is the current flowing? Well, because of Ben Franklin, we say the current is flowing this way. Now, we know that's not true. We know the electrons are actually what move, and they move the other way. But because of Ben Franklin, we are going to draw ours in this direction. This is sort of a simplistic diagram of a battery. This is really more of almost like a picture of a battery. If I was going to draw a circuit, like what we're going to draw in this class mostly, let's go and take a second to draw something like that. Okay, this is actually the same exact thing. It's just drawn differently. Instead of our wire being a loop, our wire is in perfect right angles. And this little thing, this little zigzag here, is a resistor, which also can be thought of as a light bulb. Light bulbs are resistors. And so I had the positive on this side and the negative on this side. Same thing here. I've got my positive on my left, my negative on my right. That doesn't really matter. That you can really go either way on that, but I'm just comparing the two diagrams. And so now if I were going to draw what direction things are flowing, we would draw our arrows would be going this way. And that's the conventional way that they would go, the positive to the negative. Of course, we know what actually happens is they go this way. But Ben Franklin thought it was this way, and so we're going to stick with Ben says. And that's what we're going to do. Just to take a second to talk about batteries. What is a battery? I wonder if you have in chemistry, if you have created batteries. A battery is a series of chemical reactions coupled together. A battery is several reactions connected in a series, and then a single cell is one reaction. A dry cell battery uses a paste as the reaction medium. There are also things called wet cell batteries. There are things called gel cell batteries. In any case, that's what a battery is, and you may or may not have done that in chemistry classes, created a battery from a chemical reaction. But when we talk about in this class, we're going to stick with DC, that is direct current. We are not going to do alternating current. We just stick with DC. AC would be in physics too. So in the direct current, the charges move only in one direction, and we've been talking about that. And so here is a little bit of a diagram I was talking about, like maybe in chemistry, that you have a carbon, you've got different electrodes, and this one's made of carbon, this one's made of zinc. We have a sulfuric acid solution here, and we've got two terminals. So this is our positive terminal, this is our negative terminal. Let's look over here to this text box. Different metals have different affinity for electrons, so one will pick up electrons from the electrolyte better than the other. An overall positive charge will collect on one electrode and a negative charge will collect on the other, resulting in a potential difference. And so again, I believe you've talked about affinities in your chemistry classes. So that's just an example of visualizing chemically what is happening within a battery. In this class, we don't need to really get into that. We're just going to be looking at the current and how the current is flowing, not necessarily the chemistry of that current. When the terminals of a battery, the source of electrons with potential difference, are connected, current will flow from the high potential to the low potential, similar to the opening a hole in a dam. And so we talked about this a little along the way. You've got a battery, or you've got a wire, or whatever it is, and you've got your positive node and your negative node, and you've got potential. It's ready to go. It's loaded. It's charged. The battery is charged. And so as soon as you then connect those with a wire, then they'll start flowing. And so the amount of current is the speed of the charge flow. How fast are those electrons moving? Depends on how bad the electrons want to get to the other terminal and what is in their way to slow them down. Okay, so we will be investigating and building some circuits and seeing what happens with the energy flow with different circuits. So we'll be doing that in class so you can see that. Today was really just an introduction to that. Some things you might want to write down in the summary, because we really have covered a lot, is one thing we've talked about is current. And the formula for current is I equals delta Q over delta T. That's charge over time. And that is measured in coulombs per second, which is also known as amps. So current has an I, it's measured in amps. Also, we talked about that the negative electrons move, but we draw the arrows in the direction of the positive, or the protons, moving. Even though we've figured out along the way that it's not the protons that are moving, it's the electrons, we still rely on that old convention of saying that the protons are moving. We will, like I said a minute ago, we will in class work on several labs and activities where you'll get to see what's going on when this current is flowing.